Good evening, everyone. Welcome to our second day of our workshop. We are going to continue with Engineer Amr. As yesterday, please write any questions you have in the chat box, and when possible, Engineer Amr will discuss them all with you. Thank you, and Engineer Amr, we can start.
Okay, you are sure that you accepted all the attendees, okay? Okay, here's the screen shared. I'm right. Everything is good.
Yes, all is fine.
Okay. Uh, so, good morning, good evening, good afternoon for everyone. Uh, Today is the second day in the workshop of practical reservoir simulation. Uh, I'm insisting to repeat this code, keep it simple, clean, controlled, and realistic for any model you are doing. So, yesterday we discussed the reservoir engineer's objectives and integration, and an overview about reservoir simulation, and to remember the three whys why we are doing reservoir simulation, where we can do the reservoir simulation, and what is reservoir simulation. And now we are يعني describing the or how the simulation model approach is done. And we started with the terminology of IFS or the integrated field study. What is the integrated field study? And we started the reservoir static modeling. Sorry. Today we going to explain and discuss the dynamic modeling workflow as an overview, and the reservoir simulation formulation and nonlinear linear conversions. And this topic I know that many people afraid from, but hope to after this session you discover that it is very, very, very easy and simple. And then we are going to describe the dynamic modeling initialization. What does it mean, and how we can make a initialization for the model. And finally, today we are going to discuss the model initialization input, the rock physics. And tomorrow we will continue with the fluid properties and dynamic modeling common challenge and solution. And again, we are going to talk about interactively the in the case study, and if anyone has question and answer. And before that, there is an overview in case of project. If I have fulfilled the project simulation, so it could be done in 6 months or 1 year, so it has to be managed as a project. So in the project management of reservoir and simulation or integrated field study, how it could be. So let's start. Before I start, sorry, I have to mention that all models are wrong, but some are useful. Another slogan that you have to put in your mind, that all models are wrong, but some are useful. So what we are saying here, or what I'm trying to put it in your culture, in the reservoir simulation, that the objective is the model that you are going to do is it could be must be useful. So briefly, yesterday we talked about structure modeling and fishes modeling, and then petrophysical modeling, and how we make many multiple realizations so we can calculate the volumes and make uncertainty to create P10, P50, P90, and visualize the end product. And yesterday we discussed that in structure modeling, the uncertainties or the errors or the uncertainty first come from the horizons and the how you make the layers and resolution. Describing or elaborating the real geology, and also the in fault system or stratigraphic and the trends, all of this, but concentrating in structure. So the structure model uncertainty come from it, but a fault system, doing fault system using pillar gridding or pillar gridding from the structure framework, it must be doing in the right way so we can have errors later on in the dynamic. And then we discussed in fishes modeling the how the distribution of fishes modeling and the rule of the fishes modeling. It's about a lithology. All of the fishes modeling is about the lithology or the sedimentology of the model, or we can make rock types. And finally, in petrophysical model, how we can distribute the properties depending on the wells that we drilled, and as much as we have from wells, the uncertainty of course will decrease. And finally, it was my advice to go to look for the Kriging and the SIS and SGS Gaussian, and look for these three topics. And the key word here is called variogram, and something called nugget and cell and the range. So you have to understand it very well before you make any fishes or petrophysical model. So we start. Now we have imported the static geological model and build a simulation grid. And we will go to the next step or next phase in simulation modeling. The first step could called upscaling properties. And I told you yesterday that in upscaling, our target is to make the minimum cells that respect the geology. So you have to make the minimum to, but and these grids are for the flow, to ensure the flow when you make the dynamic. So, and make it fast as much as you can without any complication. So you have to make the less cells. So here the upscaling we can, after I made the static model with maybe I have to in the static model to make very minor cells, so it could be in detailed. But after that, as a dynamic, I have as an example a shale zone with three layers. So these layers will be converted to cells. No need for these three. I can make coursing or upscale. I can average these three layers to one layer. So, and the other challenge that I can make upscale, so I can averaging as an example four cells in one cell. But here I can make this average wrong. So if I have a thin layers of with different in rock types because of in geology erosion or something, or unconformities. So in averaging, I will average something like zero point 0.2 porosity and 0.5 porosity. So the end cell that I'm averaging is not realistic. So in upscaling, you have to take care of the resolution, and you have to take care of what you are make this upscale. So here, as an example, if I have a porosity and maybe I have four cells or 10 cells and I will make it in one cell, I have to make an arithmetic average of all. So the upscaling is the is coarsening the cell without affecting the property or geology. Keep it this in mind. In the permeability, we can use a directional flow by averaging our net to gross ratio, something called volume weighted averaging. Is all the simple statistics. So upscale cell that will not affect the conceptual model, but decrease the calculation process. We have to decrease the calculation process. So the simulator, as you saw yesterday, a lot of equations solved in Kriging and averaging and Gaussian and function. So my rule here is to minimize this calculation. So if I have a complicated or complex reservoir, as an example in the fluid, if I have reservoir, I have to simulate two-phase or three-phase model or a gas condensate model. You will see that a lot of composition will change with pressure. All of this is our equations. So my rule here is to minimize these equations as much as I can. So this is about the upscaling and about the rock and fluid properties. In reservoir simulation in dynamic modeling, before I made the initialization approach, I have to insert in the model that I have the SCAL or special core analysis data. The special core analysis data done in the lab to give me relative permeability curves and capillary pressure curves with saturations. From them, I can expect the irreducible water saturation, that the water saturation that is not moving, and the residual oil, that oil that cannot move. So it's a function in saturation. Also, I have to put the capillary pressure, and you will see why. It's very, very, very important. It's crucial in reservoir simulation. Also, I have to put in my model the PVT or fluid properties of the fluid itself that I'm going to simulate and produce, whether it is volatile oil or gas condensate, dry gas, or something. So in single phase or single, as I mentioned yesterday, if I have a single phase reservoir, it could be easy. It could be actually run analytically. But if I have something like volatile oil that with production decline, with pressure decline, I will have to phase, or something like gas condensate. So I have to put in the model the composition changing with pressure. So we must now have a deal that yesterday all of properties that I inserted is static. It's not changing with pressure. But in dynamic, everything changes with pressure, that it changes in time step. This is why it's called dynamic. Okay, so what changed with the pressure, saturations, so relative permeability, and the capillary pressure, and in fluid, of course, it will change with pressure in form of viscosity and density and formation volume factor and all of that. All of this tables I have to insert in the model. And then we will go through the milestone of reservoir simulation called initialization. What is the initialization? Simply, and we will go in details after this slide. Simply, the initialization is the distribution of the pressure and saturation all over the model. How? The initialization, you will see that it could be done by something called equilibrium, or could be done by something called enumeration, which is not used, of course, because it will give a lot of errors. You will see in details how it could be, but to know as an introduction in initialization, you have to put a depth, could be a datum with a pressure as an input, and then the model will distribute the pressure vertically up the datum and down the datum. Then in dynamic model, after making this initialization, we have to define the wells and control. The wells that drilled in the field, of course, when we made a model, it's according to the X and Y, or the coordinates of the map system. So you have the X and Y in your model. So you have to insert all the models, or the well models, and the right location, and then something called control. When you produce in the simulation the wells, you have to control this well. Like in real, you can control it by choking or switch on, switch off, anything. So in model, the same thing. You control, so that you can control the rate. tell the model I need to make a constant rate, a plateau rate. So the model have to simulate the pressure depletion in the reservoir with this rate, or the vice versa. I need to control the pressure as I have an active aquifer as an example, and see the rate how it will be simulated. So the after I make the initialization, I have to define the wells and the control in the wells in the dynamic model. And here I want to, before we go through this workflow, in initialization milestone step, when the static model is finished, we agreed yesterday that I have an output of volumetrics. I have the volume. After I made the initialization, putting in the dynamic model, the capillary pressure, the relative permeability, the datum, the pressure, the saturation distribution, all of this, it will give me a volume according to the curves and the new data that I insert. I have to get the volumes of the dynamic and compare it with the static that was done by the G&G department. If they are matching or have an uncertainty with 10% or deviation with 10%, okay, it's allowed. But if it is not, there is a very big difference. So I have a problem here. I have a problem you will see in the capillary pressure or relative permeability curves, or something called end point scaling. So it's a milestone. The first thing to make in the initialization is to check the volumes that is an output of the initialization of the dynamic model. Okay, I will continue. After I make the define wells and controls, I will run the simulation, and the final product of the whole reservoir simulation will be these beautiful four charts. If you see these charts, it's gas production, oil production, and deep pressure. So as an example, here is the, if you see the dotted and the continuous line, something called the history match. That the dotted, I think, is the history, the history of the field, and the line is the production that made by the simulation. So in that case, in this chart, tell me what? Tell me that I have done a beautiful work, that it's matching. The production is matching my model, simulation model. So my model could have the credibility to continue with forecast, or if I need to test it an infill well, or water injection or gas injection or something, I can do it. So this is the history match, the final product, comparing the real field production to the simulation production. So after that, as I mentioned, I will do my forecast, adding my infill wells, and I have a model like the is useful. It's not 100% right, but it's useful. I can depend on it in decision making in the future, and not to drill as an trial and error, or guess work as that I told you yesterday. No, it's a model that I made, and I have an history match, and I can decide the infill well location to optimize the production from the field. Okay, here is the briefly the workflow of reservoir simulation. We will start before the initialization step, the first step in the dynamic model after the upscaling. That it is the upscaling step is between the G&G and the REs. Here the first step is initialization. But before we go to initialization, we have to mention or understand the how reservoir simulation depend on as how it works, how reservoir simulation works, the calculations in the reservoir simulation, how it works. It depends on something called diffusivity equation. Okay, please concentrate with me, because it's very simple, and I found that many people found it very complicated, but it's very simple. Okay, so diffusivity equation come from diffusion equation. And diffusivity equation is a kind of cold. I will describe it in the next slide. I will elaborate it in the next slide, called PDEs, partial differential equation. So, if you remember yesterday, I told you something in any simulators depend on three methods. Something called finite element method, like in well test, and finite volume method in reservoir simulation, and finite element method like heat and all of this, and thermal and another simulation. So here in the reservoir simulation, we are dealing with finite volume method. But actually, it's not a volume, it's a mass. And it's very important to focus on that. The reservoir simulation calculation depend on the conservation of mass. And we have in the 16th century French chemist, very popular, called Antoine Reservoir, Laurent. This chemist have a law of conservation of mass, or principle of mass, which it is close to all incoming and outgoing transfer of matters. What he said something called continuity equation. What is continuity equation? It is a very simple equation. Continuity equation said that the rate of mass accumulation equal mass in minus mass out. Okay? Mass in, mass out from the cell. So what will remain in the cell is the accumulation. So it's very simple. That's why, and from here I will go to diffusivity equation. Diffusivity equation, or 3D Cartesian equation, because we have another thing called the radial diffusivity equation. It depends on the shape of the cell. Diffusivity equation, it is equation, general Cartesian pressure diffusivity equation, that depend on the continuity equation or the mass balance equation and Darcy, that we will see, Darcy's law. And there is a very big conflict that I found, that many people thought that the mass balance is a material balance. No, it's not. A very big difference between mass balance and material balance. What are the difference between the aspects? As an example, the aspect of scale. The mass balance is a mass, but material balance is volume. So the difference between them, something called density. Density is mass per unit volume. So in reservoir simulation, we are dealing with mass balance. You will see in the, if you go to search in the PVT, it depends on the mass balance, not the material balance. Okay, so the mass balance is a PDE, partial differential equation, but material balance, it's an algebraic equation. In terms of pressure, the mass balance varies in space, but in material balance, it's a single average pressure. In simulation, we are depending on mass balance. We are not depending on the material balance. For history matching, the mass balance is a grid based, but in material balance is something called, we are dealing with, is called tanking model, made by, as a material balance made by softwares, as an example, called MBAL or something. It is a material balance equation, 1D, not describing cells, but it describes the reservoir as a whole object. And also, of course, in the forecasting, in the mass balance detailed, but in material balance it approximate. Yesterday I told you that sometimes we need reservoir simulation to know the forecast of well by well. But in material balance, yes, you can do it, but it's an approximate job, not a detailed job. The difference between mass balance and material balance. The second thing I want to highlight before I go to the continuity equations, something called ODEs and PDEs. I'm trying to make it simple. Huh? The ODEs, or it's an ordinary differential equation, but the PDEs are called partial differential equations. And I know that I have here, there is attendees not didn't study this mathematics. So I'm trying to keep it simple. What is a differential equation? As an example, when I said that velocity, that we all drive cars, velocity equal distance over time. But in modeling, we are not calling like that. We are calling it is the rate of change of distance about related to the rate of change of time. Okay, it's the same terminology. So this is called ordinary differential equation. But partial differential equation, when I say that two independent variables are changing with time. Okay, so if I want to describe to have a mathematical formula that describe one independent variable changing with any variable another variable, so it's called ordinary differential equation as velocity equal to meter per second as I put it here. So it's a function in time in one independent variable. But what if I have a function that is depending on two independent variables like space or distance and time. Here the PDEs. And in our reservoir simulation, we have to simulate is you don't need to be an expert in mathematics, but you must have the physical meaning of these equations. So in reservoir simulation, we are simulating what? We are simulating flow rates in time steps and in distance. So we have two independent variable here for the flow or for the velocity of the flow, the x and the t, the distance and the time. And I'm here, I will tell you an example. Here, the two schedules that you have that you see in the bottom, the time and position. So in the velocity or ordinary differential equation, it's describing time and position. Nothing at all except the time and position. So at time 0, the position will be 5. At time 1, after 1 second, the position will be, it will move. The car will move 2 meters. And so it's a velocity that you can calculate. But in partial differential equation, there is very something strange here. Could it be the position will be 0 and time 0 and we have velocity 2? Yes, in partial differential equation, yes. I will simplify it. Imagine that you are in your home and telling your friend, when you leave your home, tell me so I can pick you up after 1 hour. What you have done now, you calculate the your friend that in his home that he will going to go to somewhere that you are going to. So you calculate the velocity that he will go in 1 hour or something. So you will pick your clothes and go pick your friend after 1 hour. Depends on the calculation. In the partial differential equation is different. It's like you are calling your friend and your friend is in his car and driving this car with a velocity, as an example, 100 or 60 kilometer per hour. And you are telling him, when you reach a certain place, tell me so I can pick my clothes and meet you. So it's the time step here is related to you. The 0 time step, the flow or the car velocity was 60. So you need here an equation to describe a space and time. This is how flow in modeling goes. And you will see in the in details. So before also we go to the diffusivity equation, we are now agree that I depend on diffusivity equation on two things. The first thing is the mass balance, that totally different from the material balance. And the second thing is the Darcy law, to have a Cartesian diffusivity equation that it is a partial differential equation. The second thing is Darcy's law. Darcy's law, we all know, I think, Darcy, or you must have Darcy before you have this workshop, of course. Darcy said that the rate equal permeability for area times delta P, or the difference in pressure over the viscosity, and delta, or the difference in in distance. And if you make another formulation of Darcy, you will find that the velocity of the flow will be equal the negative, of course, because the velocity will decrease, permeability over viscosity multiplied by this inverted delta, that is a special difference that in x and y and z of pressure, the difference in pressure. So very simple conversion we will do. that if we say that here, if we said that the rate equal the velocity multiplied by the area, so the mass will be the rate as a volume multiplied by rho. That's why I'm telling you that we are dealing with mass, not volume. The difference between mass and volume is density. So we have here something, the density multiplied by velocity multiplied by the area. But in mass flux, we are dealing with uh, almost nearly equal cells, as I told you yesterday, that you don't have يعني it's if you and this is the benefit of the workshop. As a static modeler here, if you attend, you will know how we are suffering after that in dynamic model, when the model is do not clean or in improper way. So I'm here assume that the area is the constant between the grids. So the mass flux will be the density multiplied by the velocity, and here the final conversion will be the density multiplied by the velocity will be equal the difference in pressure and the density, and the relative and the permeability and viscosity. So this is the final formulation of the Darcy. So I have here the Cartesian diffusivity equation, or the diffusivity equation, which is this formula. Why you call PDEs again? You will find that the right hand side and the left hand side. So okay, and the left hand side. The right hand side is the flux. It is the mass in minus mass out, and plus the Q if I have injection or producer. Of course, it will affect the mass. It will increase or decrease. Okay, in distance will equal mass in minus mass out will equal what is remaining in the cell. And in each cell, I will do this equation. So a lot of millions and thousands of calculation I have to make will be equal the remaining. The remaining here we are measuring in time. So the accumulation in time and the flux in distance. So here, as you remember, if you remember that in accumulation, the mass, or if I have a cell, so the cell will be the volume multiplied by the density. It will be equal to mass. So what the volume? The volume will be the volume of the cell multiplied by the saturation multiplied by the porosity that I inserted by the static model, multiplied by the density of the oil of the fluid properties that I will insert. Okay, so the difference in the this terminology, or this expression with time, we will split it. So you will have here the saturation change with time to equal zero. We assume it like zero, and we will multiplied both in this terminology with change in pressure, because I need to relate the accumulation to pressure. So it will be like this. And so it's, if we say that the density change with the time, so I'm talking about the compressibility of the fluid, and the porosity, that the compressibility of the rock. So some summation of all of that, it will be the porosity multiplied by saturation multiplied by the density, and the compressibility of rock and oil will be the total compressibility. This is how this terminology happened. But this terminology is divided by the density finally, because you will see at the end that we are talking about mass balance. So here we have an expression density, and here we will have density, and here we have density. So we will divided the density in the right hand side and the left hand side. It's a very simple mathematics. So this is how the accumulation, how the simulation calculate the accumulation in that way. Another the right hand side here, as I mentioned, that it's a Cartesian, so it's a rate of change of pressure, okay, with x. So, and here we have a differential equation from the second degree because you need in the flux you are measuring or to express the mass in minus mass out. So you will measure, or the cell will calculate the rate of change of process of pressure from the beginning of the cell and the end of the cell. This is how it works. So the flux mass in minus mass out will be equal the remaining in time. To get this differential equation, this is how it works. But all of this equation, it's called analytical equation. That's why there is something called analytical model. Like in, as an example, in well test or something, it's an analytical model. But reservoir simulation, we call it numerical reservoir simulation. So all of this calculation will be interpreted in a very simple way called numerical. So in the dynamic model, you have to notice something, of course, before I will start, that in each cell, the center of the cell will be the value of the whole cell. That's why, again, in static model, as an example, when I'm telling you, you have to make a very small cells or to have a high resolution cells in, as an example, in the field or in the place or location of the water contact. Why? Imagine if you have a very big volume cell, a very big volume cell, and the contact will reach the center of the cell, water. So the whole cell will be water. In that case, in your model, the water contact will not going to be realistic. It will be above the real contact. So that's why in contacts, you have to put in the static model, as expected, you have to put the static model, high resolution model, a high resolution cells in that place. So you have to cooperate with the dynamic before go start with the static. So in the how simulation act with diffusivity equation or the analytical simulation, it will do something like this. If I here have an x or the a cell, it's split to x divided by 2 and plus, and x minus divided by 2. And in each step or in each distance, it will calculate it like that. The delta p will be pi plus 1 minus pi over delta x, and the this part will be the p minus pi minus 1 delta x. So it will convert the analytical to numerical in form of I and j and k, which is x and y and z, and repeat all of these equations in each cell in each time step. So that's why we have to upscale the model as much as we can to optimize the calculation, but not affecting the geology, of course. And the term of relative permeability over viscosity in Darcy equation will be like here written as a T. T is called transmissibility, and the transmissibility depend on the mobility, and the mobility is the permeability over viscosity. So this is how the numerical model works. To have something, as I mentioned in the beginning, called finite volume equation. The finite volume equation is like that. So this is the finite volume method, depending on the equation that's controlled by transmissibility, permeability, and viscosity, and delta P. And storage in form of X, and the storage in form of T. So here I finished the formulation behind the model. And if you're not understanding very well or clearly, of course you will ask at the end of the of the session today, but look at again and again. And if you feel now that it's easier for you to understand, so for me it's more than enough to see how it's simple to how the calculation, how is it simple. You don't need to be afraid because of maybe some professors get it very deep and very complicated. No, it's easy. And to know if anyone here thought that the material balance is the mass balance, it's so now you are not you are now know clearly that the difference between them is density. This is volumetric and this is mass. All of this. So I think we after this mathematics we need 5 minutes break. So now it's in Egypt 7:40. 5 minutes, and I will continue with the again with the reservoir simulation, but easy things, like relative permeability and capillary pressure curves that we know. It will be a very simple also. But 5 minutes break, and I'll be back. Hello again. So I'll start the next part of the of this session after we to recap that we have the now know the workflow of the reservoir simulation, dynamic modeling. Then we go through the formulation to know the diffusivity equation as a PDE or partial differential equation that depend on the continuity equation, which is the mass balance that different from material balance, and the Darcy velocity rule. So we will start the first step of initialization. And as I told you that if you have a project, a full field simulation model, that it could take 6 months or more, the milestone of the project will be the initialization. So in initialization, you put all the inputs you inserted from the pressures, saturations, and all of this, and then calculate the volume of the dynamic, respecting the property model, respecting the structure model. But in static modeling, you inserted the water saturation to have the net to gross ratio. In initialization, we said that we can make an initialization using enumeration depending on the static model saturation distribution, but it is not practical at all. The thing that we always do is initialization by equilibrium, that we have a datum inserting the pressure and saturation, and the model will distribute the saturation depending on the pressure and the kind of fluid. As an example, the gradient or distribution of pressure, if I have gas, it will be 0.01, 0.08 or zero point 0.1. In oil, it will be 0.35. So the pressure will increase 0.35 psi per foot. And in case of water, it will increase almost zero point 0.5 or 0.45 psi per foot. So the initialization, you give a datum and pressure and fluid saturation, and it will calculate. So the distribution of water saturation in dynamic will depend on what? Will depend on something called endpoint scaling, or residual oil saturation, and irreducible water saturation. You will see. So we'll start in model initialization. Model initialization, it is a process of computing initial pressure, saturation, compositions, and phase distribution in every grid cell of reservoir simulation model, such that the hydrostatic and thermodynamic equilibrium, which is the initialization by equilibrium. All initial conditions are consistent. All initial conditions are consistent with geology, fluids, and contacts. As I mentioned, we have to respect the property and structure map and features, of course. The model is ready to start the dynamic simulation at time zero, an initial condition. Its initialization come from the state of the model in the initial condition at time zero. So, what are the variables that initialized? We initialized the pressure and saturation as WSO and SG, and phase composition in case we have gas condensate or something. So we are dealing with a simulator, not the simulation. You will see the simulator is split to something called black oil simulators, compositional simulators. In the black oil saturation, it depends on VLOOKUP tables that done in the lab. And in composition, we are dealing with something called equation of state, and to see the phase changing with the composition from C1 to C7 plus, or until C20 maybe. And at the last and the third day, we will see something called, we have to do in modeling, called lumping and delumping. The lumping and delumping, we do it to as exactly like the upscaling to reduce the number of calculations. So maybe when pressure change, the composition, which maybe it must change, so that when the composition it change, the phase will change. So the simulator here, it will be a very complex process. It will take a lot of time in simulation, need supercomputers to do it. So in initialization, again, we put the datum and pressure and the some data we will see to make this distribution. The secondary variables, not the primary variables, that will distribute also, of course, the density, because when the saturation, the density will change and the viscosity will change. How and in each saturation we will have a relative permeability of this fluid, and formation volume factor, of course, the formation volume factor, who don't know, it is the volume of the oil or the gas in the reservoir compared to the volume of the oil and the gas at the surface, and the reservoir pressure and temperature, and the difference if it go to the surface, the ambient 60 Fahrenheit and 14.7 psi, the volume will change. If it's an oil, so it will lose gas. It's in a gas, so it was compressed in the reservoir. At the surface, it will be relieved. So the volume of the gas at the surface will be much higher than the reservoir. So here the initialization. This chart could do in an operation like an RFT or RDT. How we can do it in the when we drill a well and we go with the tool to measure the pressure across the depth. So it will be like that. If you record the pressure here and here, so you will find this gradient. With this gradient, with support of the well logs, we can confirm that it's a water gradient. So in the well logs, if as example from the saturation, water saturation, or the resistivity log, tell me that it's a low resistivity formation and the pressure with this gradient, so it's water. And in this oil, we'll have this gradient. As I mentioned, the oil gradient could be 0.35, and in gas it will be like that. So in saturation by initialization, we will put here a datum, and this datum and the contacts. The datum will be at the contacts. So we will have here the datum that will be, as an example, 4,000. So if we go deep, it will increase by 0.045. And if we go shallower, so it will, the pressure will decrease by 0.35. And then we will put the datum, another datum of gas oil contact to be here, so it will distribute the saturation and the pressure according to the datum and the pressure that I give. But here the question, and another thing, it's a very tricky note. Many people don't know, and it asked many times in the interviews. In the reservoir simulation, it don't know something called oil water contact or gas oil contact. Reservoir simulation depend on the free water level. The maybe you will find it in some software called contacts, but it's not contact. It is the free water level. The difference between the contact and free water level we will see in the capillary pressure. So in the simulation, this intersection that we inserted in the model, it called the free water level. Why? Because in the free water level, the water is 100% and not movable. So it will have this at capillary pressure, the free water level, the capillary pressure will zero. And then it will distribute according to the capillary pressure distribution that I will insert it. Okay? So second thing, if we make initialization by enumeration, يعني, I need you to imagine that we will not going to put the datum and to make the model distribute itself. I will put the saturation of the static model in each cell and give a pressure, and it in this time you will never make it exactly 100% that the pressure will obey the gradient of the fluid saturation. From here, we will have a lot of errors, and the simulation will not going to be run. And the third simulation in the initialization called compositional initialization, that I told you that I have to put the composition in the initial condition. As an example, gas condensate. So it's in the initial condition will be gas. When the pressure decrease, what will happen? Some fluid, an oil or condensate liquid will come in the model. So the model must understand very well the time step and the pressure that the composition will change to form this condensation, because you will see, if you know that, maybe as an example, something called condensate banking and liquid dropout. Maybe the in the reservoir, with pressure depletion, some condensate formed in the reservoir near the well bore, so it will cause a lot of skin, and it will cause a lot of production loss. So I have to manage this, and I have to simulate this. So initialization, again, how it works. This schematic shows clearly. First, the grade and depth, the rock region, the fluid properties, contacts, and the capillary pressure and the relative permeability curve that will be in the next slides. Inputs. Then the pressure calculation from the datum will do by integration. Of course, I have the pressure and the set and the contact, and it will integrated along the reservoir vertically. And then some adjustment I have to put it in the capillary pressure, because it is the key word in the or the key the key element in the distribution. And then we'll make some checks, the bubble point, the dew point, and all of this in the fluid. Then the check the mass balance. Here I mean not mass balance as a continuity equation that we mentioned. Also the mass balance, we can say it in saturation. We had the three saturation must be equal one, so it's the mass. If water saturation increase, so the SO and SG will decrease. They must be equal one. So, and then after that, after this distribution, I have an initial state model at time zero. Common problems in initialization, some tips to understand or to know. If you are an early career and you are working, you have to focus on this. Dynamic volume mismatch. As I mentioned, that the static model have a volume, and you will put some input data as an capillary pressure and relative permeability curve, so it could estimate the water irreducible water saturation or residual oil saturation and distribute this saturation. So it's a dynamic distribution. So you could have a volume from the dynamic differ from the static. Sometimes if it's more than 5% or 10%, it's not acceptable. So you have something wrong, either in the irreducible water saturation or oil saturation that you have input, or in the static model, in the porosity and the assumption of water saturation that you have done, or maybe it could be distributed in a wrong way. Not another issue, pressure mismatch between layers, that after the static model and you put this initial and you put your input to make the initialization. If there is something wrong, you can find as an example a grid cell of water beside a grid cell of an oil, uh, or because of the cell upscaling. If you have an upscale, as I mentioned, and the contact will very big cell, and the contact will reach the half of the cell, so at the rest of the cell will be water saturated, and beside it maybe you have an LGR or fine cells, so you will have this contradiction. Don't put wrong contacts, of course. Again, unphysical saturation, as I mentioned, large initial transition, that transient initial shock. Be aware, or be you will see in the permeability inserts. Never make a shock in a model. So you can't go through any geologic feature. So the permeability in a cell will be, as an example, 1 millidarsary go to a permeability a cell, another cell with permeability 100 or 200. This shock will cause a lot of something called non-linear conversion or linear conversion that will have problems in the model when you run. Last thing, water appearing instantly in producers. If you have a mismatch. As an example, if you run the model and observe in some wells that the water breakthrough is very high, so go to the relative permeability curve and correct it. So I'm talking a lot about the capillary pressure and relative permeability curves. Today, I think we have half an hour. We will talk about the first input in the before the initialization, which is will be the rock physics or the special core analysis data, and how we are going to deal with it, and what is our homework before we go through simulation in this data in normalizing. And you will see something called leverage function and all of that before we inserted in the dynamic model. And tomorrow, inshallah, we will see how we can insert the fluid properties, and finally we'll go through the history matching. So imagine that we go to the lab with 10 plugs that took from a well, and make a special core analysis data in the lab. The special to have relative permeability across the water saturation. We all know that the relative permeability is equal the effective over the absolute permeability. So it's related to the fluid. In case I have a flow in any cell with two fluids, so we have to go to the relative permeability. Which fluid will move despite the other fluid? This is the relative permeability. So when we usually in the labs, we took many blocks and make a lot of relative permeability curves. Which curve I will insert? Here I have a problem. Which curve I have to insert? And back again. That's why I'm telling you all models are wrong, but some are useful, because we are dealing with many averaging and normalizing. A second problem that we will face before the rock physics insert, something called curve as an example exclusion. What if I have relative permeability curves done from the same field from many wells I took course, and go to the lab, and I found with a very rock type, and I have a lot of relative permeability curves with a lot of irreducible water saturation and residual oil. Sometimes I have يعني it's a conventional to find that I have many rock type in my field. Each field, each rock type have its own relative permeability, depend on something called wettability, depend on the pore throat or between the grains and all of this. So which curve I will insert? Do I have to insert for each rock type a curve? So if I have, as an example, a rock type, five rock types, so each will make three curves of relative permeability. Do I have to put the 45 relative permeability curves in the model? A lot of calculations and a lot of uncertainties. This is the second problem. The third problem, the shape consistency. As I told you, what if you imagine that I have a reservoir like this, as seen in the picture, with this rock type, and in each rock type I will put the capillary pressure and relative permeability curves that will then translate to a flow of fluids and contacts. So when I run the simulation, it will never be run. It will have a lot of errors. Why? Because we have in each rock type its own capillary pressure and all its own permeability. So maybe you will find, as here, gas cells facing water cells, an error. So the how we can solve this? Of course, if we have a history match, how we can solve all of this before we insert the relative permeability curves in the reservoir model. First, something called normalized and denormalized relative permeability curves. Okay, the normalized and the denormalized. Why? Because I need you to imagine if I have a reservoir respecting the geology and have many rock types with many something called end point scaling with many water irreducible water saturation in each and oil saturation. So I don't have to put all of these curves. All I have to do is to put like this, like here. Maybe you'll say, like here. I have a lot of curves, so I will have an average. I will do the best fit of all these curves. How many it doesn't matter. So I have an averaged one relative permeability curve. And then each relative permeability curves, like here, as an example, is look at this picture, has a irreducible water saturation, different and irreducible oil saturation. So these, how can I solve this? I will stretch this area that is responsible for the relative flows to 1 from 0 to 1. I will stretch it. How? By this simple equation. So if I have here as an example a connate water saturation 20% and residual oil saturation 0.25%. So it's the endpoint scale permeability, the relative permeability of oil at the contact water saturation will be 85. I'm doing it by numbers so you can understand. And the same thing in the relative permeability of water at the residual oil. So I have this normal relative permeability curves at the right side. What I'm going to do is to, after I make one average, okay, I will stretch it to have the fluid behavior of the fluid flow behavior depending on this equation. I will do another chart between water saturation and normalized relative permeability from this equation. It's a very simple equation that is like percentage. You know, you are normalizing each value to the 100% value or the one value. And then again, we will have something like here, a relative permeability curves from 0 to 100%. And after that, I will make denormalizing. Depend on what? I will insert in my model the endpoint scales manually. That, as an example, I have a rock type fill of carbonates. Carbonates known that it could be mixed wettability or neutral wettability or water wet or oil wet. Okay, so I know that in this rock type that depend on the depositional marine deposition that it have a lot of calcium that will the wettability is different. So the residual oil saturation and relative permeability and the connate water saturation will be different. So I will insert this. Depend on what? Depend on the original oil original relative permeability curves that done in the lab. Then I have a disconformity, and then I have a silicon, a clean sand reservoir, which it by default will be water wet, as an example. So we have another connate water saturation and residual oil after the production. So I will insert these endpoint scales in each rock type and put only the normalized relative permeability curve, and the model will denormalize in each rock type depend on the EPS or endpoint scale that I inserted. That's how the relative permeability curves and endpoint scale work. There's something called Corey, the last slide. If I don't have if I don't have relative permeability curves done in the lab, if I don't have special code analysis in this field, what I'm going to do, I will go to assume the endpoint scales, and by this simple equation, I will do the Corey using the Corey equation or Corey function to create relative permeability curves. In this, the input is the some assumption and the water and the normalized water saturation again, and here is the n. What is the n? The n, if people here have experience, they will know the n is the factor that you will multiply to smooth these curves. These curves represent the relative permeability across the saturation of each fluid. So we can depend on Curie. So we can do an equation to insert the relative permeability curve with, by analogy, took a relative permeability curve from the neighbor field or something. So we have an idea or assumption about the endpoint scales, and with that we will make the same thing in the normalized water saturation, and I will do it using function. And I will smoothing or play with the relative permeability curve shape like this. Sometimes they call the S shape and C shape and related to wettability. But here is how it works. How we put the we make our dynamic model understand the fluid flow behavior in the dynamic model with change in water saturation that is a function of pressure that it differs by the diffusivity equation that converted to numerical. This is exactly what it works, how it works. So this is about the relative permeability curves, and this is how the fluid is moving related to pressure and water saturation. The second thing and the most important thing in initialization and distribution, something called capillary pressure. The capillary pressure is very simple. It is it's the pressure of non-wetting phase minus the wetting phase. What does it mean? Here I have as an example the wetting phase. It's a water wet, so the wetting phase here is the water, and here the non-wetting phase is the oil. So the pressure here minus the pressure here will be equal to capillary pressure, if you want to get it from the RDT or the pressure distribution that you have. But we took the capillary pressure curves, sorry, again, the capillary pressure curves from the lab, that they have some lab experiments like centrifuge or something to measure the capillary pressure of this core block that they have taken. So they can have a capillary pressure versus water saturation. Before I go through the capillary pressure also, it depends on, you will see that the rule of capillary pressure, it depends on the theta. The theta here, it is the wettability. If you have here, as an example, this is an XRD as an example, you will find this an angle. As this is an example from the Gulf. If you have an angle below 90, so it's a wet. If you have 90, it's neutral. More than 90, it's non-wetting. So this is the theta, the angle, and the capillary pressure depend on the surface tension. And the people who don't know the surface tension, it's very simple. It's an or in reservoir we call it interfacial tension because there is no surface in the reservoir. It's the tension that happen to the molecules in the places that have two phases. Why it called tension? As here, if you have a molecule in the same phase, so it's there is no tension on it because the molecules is attracted to the neighbor molecules. But in that case, that we have liquid and gas, or liquid or and the surface, only we have the attracted molecules in the low side, but in the high side there is no attracted because the phase is changed. So here there's something like tension. If two people grab you from both hand, you will never, well, you will do no effort. But if someone do, you will have to you will be tensioned. You will try to resist this grab. This is how surface tension work, and this is how the capillary work depend on that. When the fluid come through a solid or the grains, something called adhesive force. It could be attracted by the adhesive force by the solid. So something called capillarity happened, and this capillarity will raise the fluid from the free water level with distance. We call it transition zone according to the capillary pressure. Okay, so if I here, as an example, say that it is a free water level and this capillary pressure, an example from 0 to 40 psi or something. So at each difference from them, from the free water level, here as an example, 10 psi, 20 psi, 40 psi, it will go through the, in the dynamic model, it will go and insert the water saturation from the curve that I inserted. So it will distribute saturation until what happened? Until the capillary pressure will stay constant, and you will find the irreducible oil saturation distributed with the pressure like this. So this is how the capillary pressure work in distributing the saturation, knowing the pressure. So the important note that I told you that in the model, the free water level is the one that inserted. Then the model know the capillary pressure equals zero and will distribute, and the movability of the fluid will depend on the capillary pressure later on. So it's a function of density. And you will find, of course, if you know that if the density is close, so you will have a high transition zone. If the density is very wide as an oil and gas, so the transition zone will not exceed 5 feet or something. And here, like we said in the relative permeability curve, we use equation called Corey's equation, and we have to make a normalization or our homework when we have the data from the lab. We have to know to make a normalized curve and put it inserted, and the model will denormalize it. Same thing in capillary pressure. There is something called leverage J function. The leverage J function here is an example that I will insert the water saturation and capillary pressure, and then I need them to distribute. But here I have something that in many rock types, here will be clear. In many rock types, permeability and porosity will differ. So when permeability and porosity will differ, when porosity is differ, especially this means that the pore throat, or the relation between the fluid and the grains in high porosity, as an example, it will be lower than if I have low porosity and low permeability. If I have low porosity, so the interaction between fluid, the pores are very tight, and the fluid is attached to the grains. So the capillary pressure will differ from rock type to rock type depending on the porosity and relative permeability. That's why Leverett do a very great job, and it was significant. It depend, all simulators depend on this equation, that he convert the pore throat that I told you, or this interaction, to and translate it to permeability and porosity. So if I have the rule of capillary pressure will be equal 2 times the surface tension or the force multiplied by cosine the theta, which represents the wettability, divided by the pore throat. In model, they don't have the terminology of pore throat. The model knows the permeability and porosity. He converted to the R converted to the permeability and porosity. So when I inserted the capillary pressure, it will translate it to this function and will distribute depending on this function. And this is the proof of why pore throat is relatively directly relation with root of permeability, and inversely proportional with the porosity, root of porosity. You will find that with Darcy equation, that the permeability proportional with R to the power 4, and the porosity is directly proportional with the square of the R. So if you subtract or divided the permeability over the porosity, so the two will neglect it here too, and it will be R, this terminology will be related to the R square. So the permeability over the porosity root, it will be can represent in this function to this root. So here again, when you put a free water level, and then they need to distribute the capillary pressure depend on the relative the J function, it will distribute. All you have to put only one capillary pressure curve. You don't need to put a lot of capillary pressure curve in each rock type. You will put one, and I mentioned that you already inserted the endpoint scale before. It will distribute it depend on it. So I'm here. Maybe يعني I'm almost finished, but some checks I have to do after the initialization, and of course the volumes. Always check the rock type consistency with geologic model, that the rock types representing the geologic model. The lab data clean. No يعني the lab data must be cleaned. If there is any distortion or in the data, or the data is not presentable or something, don't use it from the beginning, because it will get you in a very big problems after that. Curves represent reservoir wettability, and that's what the wettability is, the angle, and depend on the interfacial tension forces that I told you. Data measured at reservoir stress, that the data must be in the lab measured at the same stress and the same pressure of the reservoir. And the simulation scale here, I need to mention that the simulation scale, not the raw lab scale. You have a homework you have to do before the inserted in the simulation. You have to know that relative permeability curves will control then the flow behavior. You will see tomorrow in the history matching. If you don't have a match, the first thing that will come in your mind, the relative permeability curves. If you match the water production and the pressure, and the oil rate will not matching, so go to the model and modify the relative permeability curve as an example. يعني this is a lot of example about the relative permeability. If you have high relative permeability and at reducible water saturation, you have early oil rates. Steep, this is the steep, the shape of the relative permeability, how it affects the early water breakthrough. And in Cori, that's why I'm telling you that the in Cori function, it has n is very important, that you will manipulate or modify to have the match that you need. If you have low residual oil saturation, so you will of course have ultimate recovery factor. As an example, in the field, if you have residual oil saturation as 30% and you inserted 20%, so you have a problem. There is 10% recovery factor, or more than it could be. And after water injection, of course. If you have a relative permeability of the gas high, maybe, so you will have a fast gas production as an example. So this is how relative permeability curves affect the behavior of the model and the flow. So bottom line, we can say that relative permeability affect the water cut timing, the water oil ratio slope, the gas oil ratio behavior, the pressure support, in case you will have an aquifer or something. And capillary pressure will affect the early water breakthrough in the aquifer. It will affect, of course, the transition zone. It will affect the vertical sweep behavior. All of that, it will affect it, because if you have a capillary pressure with, as an example, endpoint scaling below that you inserted, so you will have the sweep behavior, which is not the case. So finally, some يعني key takeaways that you have to put it in mind before initialization, that scale control where the fluid will sit. The capillary pressure is the distribution of saturation again. You have to know that the relative permeability is how the fluid will move. How the fluid will sit is capillary pressure. How it will move, the relative permeability. The direct impact on original oil in place and recovery factor, and the GOR is a rock type dependent. And the data from the lab must be scaled by you by normalizing and leverage function, knowing exactly the endpoint scaling, and or if you have to assume, you have to assume a realistic figures. You have to know that curless tuning, if you do, if you in this normalizing and the leverage function, if you have a curless tuning, or the if you didn't tune this, so do not look for an accurate forecast at all. So I think I finished in my time, and I'm open here for any questions and answer. So any questions? Speak. Do not
Hello.
depend on the chat. Speak.
Hello. May I just ask a question, please? Maybe two.
طبعا. Yes, of course.
Thank you. You mentioned about the rock type, which usually we possibly can call it the fascist. In practice, in practicality, um, how many fascists would you suggest to have in a model? Basically, I've seen many geologists are very much obsessed with the fascists, like 10, 12, even more fascists,
Excellent.
fascists. Yeah.
Excellent.
Yeah. What's your opinion as a reservoir engineer?
Okay, as a reservoir engineer, because as a geologist, I will have I will have another opinion. But as a reservoir engineer, your question is very clear and very good. We always suffer from that the GNG aim or target is to make the most close static model to the real. So we can if the geologist need to mimic each feature, or if he have as an example make it his interpretation according to or the fishes interpretation according to the fishes change, like deep marine then shallow, then what happened as a 10 feet of deep marine deposition, and then we have shallow deposition, and then unconformity, and then all of this will be as a 5 feet or 10 feet or something. So the rule of geologist is he need to make this, so he will create a lot of rock types to mimic the actual the actual concept. But as a reservoir engineer dynamically, yes, it could be identified, but in modeling, if the property if the property will not have a change. So we are talking about, yes, okay, we have deep marine and shallow marine. By as an example, by logic, I know that the deep marine maybe you have a porosity, high porosity. At the shallow marine, we have some bad sorting, so you will have low porosity. And after that, you will have a disconformity and again a depositional environment with low porosity and low permeability. So if I have these three rock types, and the rock type 2 and rock type 3 will have a very dirty fishes, and the porosity is very uh, low and the permeability is very low. يعني for me it's preferable to make it in one rock type. It's a rock type. Okay, yeah, we have a rock type called rock type with bad sorting despite the depositional environment. So in that case, yes, make your rock types as much as you can, be free, but to be reasonable before that. You will see tomorrow when we decide to make a project in simulation, the first thing we have to put is the scope of work of this model. If the scope of work of this model is to mimic the geology, okay, I'm okay. But if the scope of work is to mimic the fluid behavior with the production, in that case, we have to minimize the cells as much as we can to manage this model, because this model will be with you, and you can يعني, as an example, your manager or your boss or the shareholder need some idea about the field or some output, so you have to run and have a results. It must be practical and fast as much as you can. So, as an sheet Excel, if you had a sheet Excel and full of many information, but you are suffering in opening it, is not useful as a presentable Excel sheet with the minimum data that will help you. That's the answer of your question.
Uh,
So again,
thank-
am I clear? Understand
yes,
it?
very clear. I have another question as well. I don't know if somebody else want to talk, and then I will ask you again.
Okay. So, any questions?
Um, so thanks a lot for this wonderful session. So one question from my side is, now that we understand that a lot of computation is happening because of the very upscaled numerous cells that we have. So
Yes.
um, will I mean, you mentioned something like high performance computing. So what would be the RAM that is needed to run these simulations?
يعني the RAM mine is 128 minimum at least in the black oil simulation. Because I mentioned that we have two kind of simulation, kind of called black oil, and this is in the calculation is very simple that you will find tomorrow in the PVT or the fluid behavior that change with pressure. If we have one phase oil or gas, we use a simulator called the black oil. Even if we will go through gas reservoir, it's a one phase, so it's called black oil. So the computation here will be less than the compositional simulators. The compositional simulators, imagine that I will make this mass balance for each element like C1, C2 until C15 or C16. And in each element, will then compute it to see by Gibbs phase rule the phase of this behavior. A lot of simulation. So if you try something like uh, maybe the 128 RAM will not going to be enough. We need something more than that. My PC is 128, and in the compositional I'm suffering. And it could take days to make the simulation run. This is the answer يعني. But exactly I will check it and I'll tell you tomorrow. To be and also it depend on the static model need a very high performance RAM, huh? Because you visualizing a lot of information, so you need a Vega, a super Vega to with RAMs to to normally visualize the static model especially.
Okay, thank you.
You're welcome. And also, of course, the processor. The processor, I can give you the model of the processors, but the workstation must be very high specs. Again,
Yeah. May I ask again a question? Thank you.
okay, yes, of course, be free.
Thank you very much for your time. A question I have always to ask is, at it's a oil water contact, for example. Let's say we have an oil water contact case. Where do you consider a contact in a static model? If a static model, if a modeler provide you with a model, where do you want him to put the contact? Obviously, we take it from the petrophysicist. But
Yes.
in terms of transition zone, free water level, or where is it you think it is? It should be. Thank you.
Okay. The GNG get their contacts from the as you mentioned, the petrophysicist have the triple combo or quad combo and resistivity log that it could easily identify the free water level that we consider that is the contact. There's not contact but free water level, okay? With the support of something called MDT or RFT pressure points that measured across the well with depth. So the in the static model, we can have a clear contact. Okay, why the static model we inserted? Because as I mentioned that in the static model, he has to put the contacts after يعني structure model, fishes modeling, property modeling, then the context, then he has to calculate his own volume. This volume is the end product with the uncertainty, is the end product of the static model. What I'm going to do in the dynamic, I will again depend on the petrophysicist and the RDT to insert the free water level, but in that time I will not going to distribute the water saturation as the static model. The static model make the water saturation model and the net to gross ratio to insert net to gross ratio model, property model, in order to create the volume. For me, I will insert the contacts, the free water levels that I get from the petrophysicist, and distribute the water saturation only by equilibrium, of course, initialized by equilibrium, only depending on the initial water, the connect water saturation, which it will be one value for all the model above the contact, and then compare. So that's why the static model need to put the contact and how they put it and why. Am I clear here?
Um, I think so. It means that the contact we are basically creating our model is not free water level. This is what I understand. Is that correct?
No. It's the in the model, the oil water contact is the free water level, which is mean the capillary pressure equals 0. The
Okay.
model not inserting, don't know what does it mean, oil water contact. In the in Petrel or any T navigator or something, you can find it called oil water contact because of or gas oil contact. But how simulator translated to himself, how it understand? No, it's a free water level. So in simulation, we are dealing with free water level, and then distribution, it depends on the capillary pressure above the free water level.
Okay, so
Okay?
it means that what we read from the logs, when the petrophysicist look at the logs and tells me this is the contact, that's the free water level. That's what you are saying.
Yes, yes,
Okay,
yes, yes,
okay.
that's yes, okay. Bottom
Thank
line, yes, yes.
thank you so much.
Oh, you're welcome. Again, any questions? Please, I need questions. A lot of formulation, a lot of things that need from you questions. Okay, my advice is if the workshop is beneficial for you, to look at the video again and slowly to understand. So tomorrow you can have questions and I will answer. So any question concerning last day, the first day, the static and fishes and all of this? Okay, thank you. And if anyone has any question, my LinkedIn profile is available and Mega Plus, of course, is available. You can write your question and it will be answered, of course. And thank you for your time. Hope that things are now clear for you or more easy or can more understand. And see you tomorrow, inshallah. Thank you. See you tomorrow.
Thank you.
You're welcome.
Thank you so much, Engineer Amr. Thank you everyone for attending. We'll meet you again, same timing tomorrow. We'll wait for all of you. Thank you everyone and have a good day. Goodbye.
Goodbye.